Okay, welcome everybody. Today we talk about the last topic in this course, parametric equations. Today we'll talk about the basics of parametric equations, and then tomorrow, or the next video, we'll talk about the calculus of parametric equations. And then you are done learning new material, and you can just focus on getting quizzes, projects, homework, everything done, which leads me to my first announcement and only announcement. Quizzes, homework, projects. Everything's in my open math for you to work on. Reflective writing assignments, make sure you're working on those. Make sure you check the grade book and check your grade. Make sure you're getting credit for things that you've done. If you have a zero anywhere, make sure you check it, see if you did it, and make sure you're getting credit for what you've done. Okay. So ultimate deadline for this course is the day of the final exam, which, if I remember right, I think is the 21st, May 21st. I'll have to check that. Um, Let me pause the recording and I'll check that. Yes, the final exam is May 21st at 8 a.m. Now, there's no final exam in this class. It will just be time set aside. Someone will be there. Maybe me. We'll probably maybe me. We'll see. But someone will be there for you to come in and take quizzes, work on projects, ask questions about anything. It's just one more 2.5 hour chunk where you can come in and get whatever assessments you need out of the way to get whatever grade that you want. Okay, so that's that. Make sure you have any questions that you're emailing me, and also checking Canvas for the office hours of professors who can you can go to and ask questions if you can't ask me for whatever reason. Okay. All right. So let's talk about parametric equations. So parametric equations are used in practice all the time. Um, we are used to plotting equations of the form like y equals x squared plus 2x plus 1. That's a parabola opening up, centered at x equals -1. Um, or x squared plus y squared equals 4, you're able to recognize these things now because you've practiced with them so much as parabolas and circles. But what did you do before you knew the shapes of those things? You probably created, if you wanted to plot this, or maybe you still don't know the shapes of these things and you want to know how to plot it, you throw out a bunch of x values and then find the corresponding y values and you plot those points. Remember? So, in other words, typically what you have is like one independent variable, and one dependent variable. I choose a bunch of x's, my independent variable, and then find the corresponding y's, my dependent variable, and then I can plot the points accordingly, and then connect the points in a smooth curve. Okay, but in real life, it's pretty rare for one variable to be strictly dependent on some other variable. Usually, what's happening if I have two variables x and y, they're usually dependent on some third variable or parameter, such as time, for instance. So if I think of, for instance, like the motion of an airplane, the path that an airplane takes through the sky, I could think of like the x and y and z coordinates that it's um, the path that it's taking. I could think of like z as depending on x and y, but really what's happening is x and y and z all depend on some uh, other variable, some parameter that again we usually consider time. And it's actually kind of silly to think of like the height as depending on x and y, right? Same thing with um, like the path a ball or some object takes through the air as it falls because of gravity. Like as that pin goes through the air, it's a little silly to think of like the height that it's at as depending on how far left and right it's gone. Really, as I throw it, the path that it takes, the x coordinate and the y coordinate depend on time. And like the y coordinate, the height, doesn't really depend on the x coordinate necessarily, or intuitively. Both of those things depend on something else, which is time. And so we want to describe those situations uh, using what's known as a parametric equation. Okay, so let's see how we can deal with this in practice. Let's say you run a trip, you go on a trip and run some errands, and here's the data that you have about your position at different times. So at time t equals 0, at the start of your trip, you're at 0, 0, your home base, if you will. And then at time t equals 1, you're at the point x equals 1, y equals -1, and so on, so on, so on. That's how you read this chart. Okay, so assuming you traveled in straight lines between these coordinates, let's draw a path, a plot of the path that you took on your trip. Okay, so we're going to use this graph here. I'm going to give myself uh, y-axis. Here's my y-axis, and here's my x-axis. Okay, and so at time t equals 0, I'm at the point 0, 0. So here I am, and I can even label this as t equals 0, right? And then at time t equals 1, I'm at the point 1, -1. So that's right here. This is where I'm at t equals 1. At time t equals 2, I'm at the point 2, -1. So I'm over here at 2, -1 at time t equals 2. At time t equals 3, I'm at 2, comma 1. So that is this point right here. This is where I'm at t equals 3. And then at time t equals 4, I arrive back at my house, if you want, at the origin. And so I'll say at t equals 0 and 4, I'm at that point. So if I want to plot the graph of my position at any time t, assuming that I traveled in straight line paths between these points, we get something that looks like this. Okay. And in fact, with parametric equations, we can actually do a little bit better, and we can say, hey, we're traveling in this direction between t equals 0 and t equals 1, and then we're traveling this way, and then we're traveling this way, and then we're traveling in this way. So with parametric equations, with curves defined parametrically, in addition to having some sort of curve, there's also a natural orientation for the curve. Now, that's also the case for curves that you're used to, like y equals f of x, because we usually read those things from left to right, right? But there's also a natural orientation when you're looking at graphs defined parametrically. X and Y both depend on some other parameter, t. As that parameter t increases, we have sort of a natural orientation that this curve uh, follows. Okay. So that's how we plot those points. And again, assuming we travel in straight line paths, there we go. There's the graph of our position at any time t. All right, so it is a fact that any curve in the xy plane can be represented with parametric equations. Okay. So let's say x and y are continuous functions of some parameter t on an interval I. So these things need to be known to you when you're plotting a parametric equation, a pair of parametric equations. Then the equations x equals x of t, y equals y of t are called parametric equations, and t is called the parameter. The set of points x, y obtained as t varies over the interval I is called the graph of the parametric equations, and the graph of parametric equations is called a space curve or plane curve. Or generally, I'll just put here curve or plane curve, and it's denoted by C usually. Okay. When we have a third dependent variable, z, then we will call the curve a space curve. And if anyone's interested in that, take Calc 3 in the fall. All right, so how do we plot parametric equations? Well, we could do what we did up here and just plot individual points and then connect those points smoothly. However, sometimes that could lead us astray. Let's see what happens if we try to do that with these parametric equations right here. Okay, and in fact, let me scroll up here and, well, no, let me just give myself a blank page. if I try to graph these parametric equations, x of theta, so the parameter is theta here, not t, but it really doesn't matter. X of theta is cosine of 4 theta, y of theta is sine of 4 theta. Let's try to make a table of values for this theta, and let's go by intervals of steps of pi over 4. So we'll do theta equals 0, pi over 4, pi over 2, 3 pi over 4, and then pi, and that's where we'll stop. Then x of theta and y of theta, we'll get the following. So when theta is 0, for x of 0, we get cosine of 0, that's 1. And y of 0, that's sine of 0, is 0. When I plug in theta equals pi over 4, I get cosine of pi, which is negative. That's negative 1. And then y of pi over 4, that gives me sine of pi, which is 0. Plug in theta equals pi over 2, I get cosine of 4 pi over 2, that's cosine of 2 pi, that's back to 1. Okay, so we're getting a 1 there. Sine of 4 times pi over 2, that gives me sine of 2 pi, that's another 0. Plug in 3 pi over 4, and maybe you see the pattern here. I'm going to get minus 1, 0, and then here I'm going to get 1, 0 again. So if you're not being very careful, you might be able to convince yourself that the curve that's associated with these parametric equations is just a curve that's sort of bouncing back and forth between plus 1 and minus 1. You might be able to convince yourself, because I'm getting a bunch of 1 zeros and negative 1 zeros, you might be able to convince yourself that this curve is just bouncing back and forth between plus and minus 1. But let me show you in Desmos. Desmos can plot parametric equations, what you actually get for this parametric equation. Oops, sorry everybody. To plot parametric equations in Desmos, use t always, but you can just plot the parametric equations, the x and y functions, as a point in Desmos. So let me show you what I mean. We're looking at cosine of 4t, comma sine of 4t, for t between 0 and 2 pi. And there we go. There's the curve that we actually get in this in Desmos. Okay, and in fact, let me show you. If I put a little slider in here, a that goes from 0 to 2 pi, then we can actually even look at what happens as the parameter increases. So as t increases, we're wrapping around this circle. So these parametric equations actually wrap around this circle 4 times. That 4 tells me it's wrapping around 4 times, which is interesting. 1, 2, 3, 4. 1, 2, 3, 4. Wow, amazing. Okay, so that's the actual curve that we get here. Okay. So we need a sort of a better way, how do you know when you're plotting points and connecting the points smoothly? How do you know that you're capturing all of the behavior of the graph that you need to be capturing? And the answer is you don't if you're just plotting points. Plotting points is great for getting an idea, sort of a rough idea of what the curve looks like, but what we want to do a lot of the time is take advantage of what we've already learned about graphs of functions. So one of the best ways to plot a parametric curve is to try to eliminate the parameter to end up with one equation involving only x and y. Okay, so try to eliminate t, or in general, eliminate the parameter. To end up with only one equation involving x and y. So let me show you how you do this with this equation here. There's sort of two strategies. There's a multitude of strategies depending on what your particular parametric equations looks like. Okay, so for something like this with cosines and sines, I'm usually going to try and take advantage of the Pythagorean identity. Okay, so let's try to look at so let's look at this example here of x equals cosine of 4 theta. We just saw in Desmos um, that we should get a circle here. Let's see why. I'm going to remember that cosine squared of anything plus sine squared of anything equals 1, right? And so in particular, cosine squared for theta plus sine squared for theta is equal to 1. But notice, cosine squared theta, that's the same thing as x squared. Sine squared theta, that's the same thing as y squared. And what's that the equation of? That's the equation of a circle. Okay? Now we do need to know, so technically we need to be careful. We need to make sure we know what values of the parameter we're actually looking at. But this tells me that the curve, the parametric curve that is defined by these parametric equations, lives on the circle of radius 1. Okay. I need to do a little bit more investigating to see how much of that circle we're tracing out, but it tells me that the parametric equation, the curve defined by this parametric equation, lives on this circle of radius 1. And as you can see, that's the circle that we get, right? Circle of radius 1. Amazing. So let's practice this with another example. Now, a lot of the time, eliminating the parameter is just going to involve like literally solving one of the equations for t and plugging it into another equation. So let's do that here. Let's plot the curve given by this parametric or this pair of parametric equations. Okay. So something to always keep in mind again is going to be really important to note the um, interval that t lives on. That's going to tell us what part of the graph we need to keep here. Okay. All right. So let's eliminate the parameter here. Eliminate t. Okay. So this tells me y equals t minus 4, and this tells me x equals t squared. Right. A lot of the time is convenient to drop the x of t and y of t and just work with y equals blank, x equals blank. Okay. Now, there's one of two things you could do. You could solve for t here and get t equals the square root of x. But when I take a square root there, I should do plus or minus, right? And that plus or minus is messy. You could work with this and then plug that in over here and get y as a function of x. But again, that's a little messy because of the plus or minus. So what I'm going to do instead is this equation is much nicer to solve for t. This tells me t equals y plus 4. And I'm going to plug that in there into the equation for x, right? And this tells me x equals, well, t squared, that's the same thing as y plus 4 squared, which is a parabola opening to the right, opening to the right with vertex at 0, -4. So let's go sketch that graph. All right, and we need to be careful when we're doing this. So here is my x, y plane, and we got a parabola opening to the right. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7. Opening to the right with a vertex at -4, or sorry, 0, -4. So I know I've got a vertex here. And then it's also convenient to figure out, when y is 0, what do we get? Well, when y is 0, I get x is 16. So let me go by twos here. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so when y is 0, I'm getting that right there. When y is -3, I'm getting x equals 1. So I'm getting that and that. So this is a pretty stout parabola. So now that I've plotted a few points, let me connect them all smoothly. I'll use blue here. Okay. So here's what this parabola looks like. Pretty rough sketch. Now, this is not the curve that we want. We know that the parametric curve lives on this parabola, but we don't want the full parabola and just call it a day. What we want to do now is plot only the part of this curve defined by the parametric equation. And that's where this interval comes into play. T is only between -1 and +2. Okay, so when t is -1, what do I get for x? I get x is +1, y is 2 minus 4, that's -2. So when t is -1, we get, wait, what did I just say? I'm sorry, everyone. When t is -1, we get, I'm putting in -1. X is 1, y is -5. There we go. So we're getting this point right here when t is -1. Let's think about what we get when t is 0. So now that I've given myself that curve, now it's totally fine to plot some points for different t's so that we know what orientation this curve has. When t is 0, we get x is 0, y is -4. So here's what we get when t equals 0. When t equals 1, we're getting x is 1, y is -3. So there's when t equals 1. And when t is 2, we're getting x is 4, y is -2. So my scaling's pretty good there. So let me draw the actual part of the curve that we want. We only want this part of the parabola. Okay. And again, it's also pretty convenient to put in orientation there. Now that I've drawn that, erase the rest of the curve. We only want that part of the parabola. Okay. And that is how you can eliminate parameters to figure out, again, where your parametric curve lives, but make sure you're taking into account the interval of the parameter, the domain of the parameter. So let me switch to Desmos so you can see this parametric curve now. The parametric curve t squared, t minus 4, for t between 0 and, or sorry, -1 and 2. Zoom out a little bit, and there you go. Our scaling was a little bit different. Our scaling went from 0 to 16, and from about -7 to, we'll go about 1 there. And you can see now that I've scaled things more similarly to what we sketched, we get a much better looking curve, something that looks closer to what we sketched by hand. Okay. So that's eliminating the parameter. One thing you can always try is solving for t with one equation and plugging that t into the other equation to get a one curve, or sorry, one equation, two unknowns, which you know how to plot that for one equation, two unknowns. Okay. All right. So that's eliminating the parameter. Amazing. So everyone, take a second, pause the video, and try to eliminate the parameter here. The parameter is theta. Hopefully you eliminated the parameter. I'm going to rewrite this as x equals, oops, get out of here. X equals 8 cosine of theta, comma y equals 8 sine of theta. I again want to use the Pythagorean identity, x squared, or sorry, cosine squared theta plus sine squared theta equals 1. That's what I want to use. Okay, so I'm going to divide both sides of the first equation by 8, I get x over 8 equals cosine of theta. And divide both sides by 8 over here too. And so this tells me, well, cosine of theta is x over 8. So I get x over 8 squared plus sine of theta is x, or y over 8. That equals 1. And now I can sort of distribute it a little bit. This is x squared over 64 plus y squared over 64 equals 1. And so x squared plus y squared equals 64. Okay. So again, this tells me not necessarily that the curve I'm looking at is the full circle of radius 8, but it tells me that this curve we're looking at lives on that circle of radius 8. Okay, so let me sketch that circle of radius 8, and then we'll evaluate the parameter at a couple of different points in the interval we care about to make sure we're getting the full curve. Okay. All right, so here's x, here's y, 2, 4, 6, 8, 2, 4, 6, 8. Here's the full circle of radius 8. Should have drawn that in blue. Let me draw that in blue here. Oh, there we go. There's my full circle of radius 8. And now we, again, evaluate the parameter at several different points. So when theta is 0, I get x of 0 is 8, y of 0 is 0. So I get this point right here when theta is 0, theta equals 0. Let's look at theta equals pi over 2. We get x of pi over 2 is 0, y of pi over 2 is 8. So we get this point right here when theta is pi over 2. When theta is pi, I'm getting this point over here. When theta is 3 pi over 2, I'm getting this point over here. And when theta is 2 pi, I'm getting this point over here. So we are getting the full circle traced out exactly once. So I'm just going to leave it like that. And again, we can see this in Desmos. I do 8 cosine of t, 8 sine of t for 0 between, or sorry, t between 0 and 8, we get this. And maybe you see that if I change one of those coefficients, take a second and think about how that would change the shape of this. If I change this 8 to, say, a 3, think about how that would change the shape of this. Hopefully you see that it would make the circle is going to squish it down into an ellipse that goes left and right still to 8, but up and down to 3. Okay. Wow. Okay, so that's how we can use parametric equations to um, uh, trace out a circle or an ellipse that's either wider than it is tall or taller than it is wide if you want. Okay. Pretty cool stuff. Parametric equations are very fun. All right, so we're going to finish with what's known as the cycloid. So a cycloid is the shape that's traced out. Let me change to black here for a second. The shape that's traced out if, let's pretend you're a bug on a bicycle, okay, and the bicycle has a radius of 1. So here we go. Here's a 1, and let's say the bike is, so that's actually a little too tall. Let me scooch this down a little bit. So let's say you're a bug on a bicycle of radius 1. Very fun to think about. Okay. And let's say initially you're at this point right here. And here's the idea of the cycloid. The cycloid is the shape that is traced out if you hold on for dear life to the bicycle wheel. The shape that you would, or the path that you would trace out if you held on, that path is known as the cycloid. So let's think about what it would look like. As the bike moves, it moves a little bit, so it rolls a little bit. So what would you do as the ant? You're holding on for dear life. the point where you were touching, well, you're not just holding on to that one point. It rolls, it rotates, and you are over here a little bit, right? So as the bike rolls to this point here, you've traced out that bit uh, of a path, right? So we want to actually, so it should look like something like this. It's going to look like a sort of a bouncing ball path, right? We want to figure out what that path looks like. This is a fun first kind of difficult parametric equations problem. And so to do this, let's think about the coordinates of the center of the bike tire, and then your coordinates in relation to that center. Okay, so I'm going to call these coordinates, um, let's call them x of t, y of t. And let's say the bike is moving to the right at a speed, a linear speed of 1. Okay, so what does that mean for this center? If it's moving to the right at a linear speed of 1, well then what is that those coordinates? Well, first of all, the y coordinate of the center is always just 1, right? This has a radius of 1. You're always at the center of the bike is always at a radius, or sorry, a height of 1. If the bike is moving to the right at a speed of 1 unit per second, then that means that if I call t seconds, the center of the bike is at a distance of t, right? If I'm moving to the right at a rate of 1 unit per second. Okay, so we'll say that that's the center of the bike after t seconds. Okay, all right. So there's the center of the bike. Now, for us, in relation to the center of the bike, we're going to need to know a couple of things here. So let me draw in a certain special right triangle. Okay, we're going to need to know what angle has this bike rotated through in terms of t, right? What angle is that? If we can figure out what angle that is, then we can figure out all the side lengths of this triangle, because this right here is just a distance of 1. So if I can figure out this angle in terms of t, then we're basically done. Okay, now if the bike is moving to the right at a speed of 1 unit per second, so the center is at a uh, uh, point of t comma 1, then what does that mean about this distance here? That distance there is the same as the arc length here, right? But that distance there is t. And hopefully you remember from a pre-calculus class that arc length, s, is r times theta, right? So if I can figure out theta, then I can figure out the side lengths of this special triangle, which will get us the rest of the way there. Okay. The actual coordinates that we want are the coordinates of the bug, which I'm going to call now. Um, I, I initially called the center x of t, y of t, but then we figured out what that was right away. So now let me call these coordinates x of t, comma y of t. Okay. All right. So if I've traveled a distance of t, that means this arc length is also t, because the radius is just 1. So we have t equals 1 times theta. In other words, theta is just equal to t. So this theta right here is t. And so now, because I know that this hypotenuse has a length of 1, I can say what this leg is and what that leg is, right? Let me do this in color. We'll color this blue. The blue leg, the length of the blue leg is, well, that's opposite to the angle theta, which is t. So sine of t is the length of that blue leg over 1, which means that that blue leg just has a length of sine of t, right? So that means x of t, right there, is, well, what is it? That's this x coordinate right here. But that's the x coordinate from the set for the center of the bike wheel minus sine of t, right? It's this distance minus this distance. This distance is just t. This distance is sine of t. And so we have x of t should be t minus sine of t. The coordinates for the center minus what we got from that right triangle. Okay. Now let's do the same thing with y of t. What are the coordinates there? Well, this distance is going to be this full distance minus that distance. But what is that distance there? Well, that distance is given by, let's do that in purple, I guess. That distance is, well, that leg is the adjacent side length, right? So that's cosine of t over 1. Cosine, well, really cosine of t is that length over 1, which means that length is just cosine of t. Okay. So again, we want this distance, which is this distance, which is 1, minus that distance, which is cosine of t. And so we have it. We have our parametric equations for the cycloid. T minus sine of t, comma 1 minus cosine of t. Now, this right here is genuinely very, very difficult to try to eliminate the parameters. So let's just go to Desmos and see what the graph looks like. Again, we feel like from our intuition for what this should look like, that this should just be some sort of like bouncing motion. Let's go and check. Here we go. T minus sine of t, comma 1 minus cosine of t for t between 0 and let's go 4 full rotations, which means 8 pi. Ooh, look at that. There's our bike. There's our bug's path. Wow, this curve is known as the cycloid. Okay. And in fact, if I draw in a circle um, of radius 1 at a center of um, what? T comma 1. So that looks like, I'm going to give myself a slider, A. A equals 0 for a second. 0 less than A less than 8 pi. So A is going to act like T for me here. So we've got what? X minus A squared plus y minus 1 squared equals 1. There's my bike tire, and so it can like move back and forth with this slider. Okay. And then A is acting like my uh, T again. So I can look at the coordinates of the bug are going to be A minus sine of A, comma, 1 minus cosine of A. So there's my bug. And so we can see how my bug rolls along, is very fun, rolls along on this bike tire. Okay, so let me make the y-axis a little better. -1 to, I don't know, let's go 3. Let's go 5. Let's go 7. There we go. And there we go, zoom square. Okay, so if I want this to go longer, I can, but here's, let me go back to the beginning. Here's what this looks like. Ooh, the green dot is our bug, the blue circle is our wheel, and we can see that that path being traced out by the green dot is in fact the cycloid, that is the path that we wrote down the parametric equations for. I could watch this for a really long time, but I'm not going to. There we go. All right, so that's how we use parametric equations to figure out, or that's how we can come up with parametric equations in sort of a complex situation like this. And in fact, it is much more straightforward to try and think about this in terms of the parameter of time instead of trying to go directly to an equation for the path here in terms of x and y. It was much more natural to think about the coordinates of the center of the tire and how they relate to the bug, um, and also time itself, right? So without parametric equations, trying to write down the path that this bug follows is really difficult. But with parametric equations and thinking about things in terms of some other parameter, it becomes much nicer and much more doable. Okay, so that's parametric equations. Next time will be the last lecture of the class. We'll talk about how do we do calculus with things like this. So how do I find, once we have the parametric curve, the curve defined parametrically, which would look something like this, right? Once we have something like that, how do I do things like find tangent lines or find the area underneath this curve or find the second derivative of y with respect to x, right? So we'll talk about that next time, and that will be the final lecture of the course. And then the week after, so you'll have a week where you can just come in, do quizzes, work on projects, and then the week after, you'll have uh, finals, I think. I think the week after is finals week. So you'll have basically 2 full weeks ish of being able to come in, do quizzes, and work on whatever projects and homework you need to. Okay. So thank you all for your attention. Keep your eyes peeled for the next video. Should actually already be up by the time all these are published. Um, and I'll see you guys when I see you.